So hello everyone. Um, so we'll keep on the things we talked about last time. Hopefully I will clarify also things that were not that understood regarding the Magic Square game, and then we will understand where all these self-testing games get into the mix. So let's recall that after Guy's talk, and I have undid, I have undone the reduction of a guy from polynomially many players back to 2 players. Okay. So the concept is the following. If we have a succinct 3-sat instance, so we have this Boolean formula F, and this Boolean formula F describes an exponentially long 3-sat instance. Then there exists a game that I'm calling G of F with only 2 players. One player that I'm calling the point player, and the other that I'm calling the subspace player. The format of questions is the following. So for the point player, I'm sending a single element inside some vector space of characteristic 2, finite vector space of characteristic 2, over a field of characteristic 2. And to the subspace player, so for this talk, let's assume that all my subspaces are just lines. Okay, this is a bit cheating, but we saw that they are either lines, maybe they are planes, or even 3-dimensional subspaces, but the idea will be the same. So we're now assuming that I'm sending them a line. And what is the format of a line? A line is just a point and a direction. Okay, and we need that the point V is on the line L. Okay, so this is the format of the questions. I'm sending the point player a point and the subspace player a line, and the point lives on this line. And I expect that the players answer with, the point player answers with polynomially many values in F2 to the T, and the subspace player answers with polynomially many low-degree polynomials on the line L. And on the polynomially many values from the point player, I'm doing all the checks of these zeros, and I check, okay, so it depends. We saw that sometimes I need to check something like that, and sometimes I'm doing another check, but I'm doing that with the output of the point player, as Guy did. So I'm checking that the combinatorial Nullstellensatz and so on. And I'm using the subspace player only to verify both that the point player is consistent with the line player, with the subspace player. So they need to agree. The polynomial that the subspace player sends me needs to agree with the point that the value that the point player sent me for any polynomial. And also these polynomials need to be low degree. Okay, so this is my last check, that the actual polynomials that I'm sent to by the line player are all low degree. Okay, so as I said last time, okay, so we have this game, and the point is that the game has value 1. The players can win it with 100% if the formula is satisfiable. And the other way around is also true, meaning if they can win with more than 1/2, okay, so if the formula is unsatisfiable, no, I want to state it like I wanted now. Okay, so if the formula, okay, so the arrows are the other way around. I'm sorry. If the formula is satisfiable, the value of this game is 1, so they can win it with a 100% probability. But if the formula is unsatisfiable, it means that they cannot win with probability higher than 1/2. Okay, so you should think of the second condition also as some as saying that even if they don't play optimally, even if they play suboptimally, if they have any strategy that beats 1/2, it means automatically that the formula is satisfiable. Okay, so this gives us some room to breathe. The fact that there is a gap between 1 and 1/2. Okay, so this was our scenario after Guy's talk, and then I stated that now we have an instance of succinct 3 sat instance. Okay, so we get now some circuit which is polynomial in length. Okay, so the input is the circuit. So we have some circuit, and it describes a Boolean formula that is potentially exponentially larger than the circuit that I began with. And this exponentially large Boolean formula describes a doubly exponentially large 3 sat instance. And our goal is to understand only from the circuit, the very small circuit C, whether the doubly exponentially large formula is satisfiable. So we get some such instance C, and we want to generate what we call the big protocol. So the concept of the big protocol is that we are going to act on it, we are going to change it a bit, such that it will become something in MIP star. But at the moment, it is in, I don't know how to call it, multi-prover interactive proof with exponentially long questions, exponentially long answers, and exponentially long running time. Okay, so this is where the big protocol.
I have a question. I cannot say that I follow. I mean, what you're saying, I follow. I don't think I have a full understanding of what's going on, but it's fine. But there is something which I don't understand.
Yeah.
Going up twice makes no sense to me. Why do we go up twice? Why don't we go up 17 times? I mean, why only 2 S's and why not 17 S's? What?
Okay, so at the end, okay, so as I'm going to show you the proof, okay, at least the review of the proof, you will understand why I'm able to do it only once. But an essential part of the MIP star is equal to RE is the fact that somehow you can reiterate this idea. And then you can do it 17 times. Okay, Nati? But as I'm going to present it now, we will see a problem at some point of doing it now twice. So for example, tackling the 3 S's instance.
This is a second step in a long journey, maybe not so long, but
yeah, it's a very large step in the correct direction, but it still lacks some virtues that enable you to go to the MIP.
Just to make sure we are not going to stop after 2 steps.
No, this is only an example of the main ideas in the MIP star.
Okay.
So let me
some point where you fix, you need to fix some ideas here to be able to do it iteratively, for example.
So let me just say what the steps are. One step, which is not trivial, is to get a polynomial time interactive proof for NEEXP. That we did. So now the next step is to get a polynomial time interactive proof for double NEEXP, for NEEXP.
Yeah, and for that we need quantum, and this is provable because it is known that without quantum provers you cannot do it.
Yeah, so this is the first step where quantum stuff goes in the protocol. Like there are quantum things to consider even for NEEXP to rule out bad, like successful cheating strategies for the provers that use quantum tricks. But yeah, so but now it's the first time that we are using quantum tricks for the truthful provers.
Okay, so I'm proceeding. So we get some instance, this C curly C instance. We just, the big protocol is just unraveling this instance. And then we get some Boolean formula F, and this Boolean formula F is exponentially larger than the curly C circuit. Okay, so it is much larger, but we can still in exponential time calculate it. And then we just play, we check what should be the game GF. We play this game with the players, and according to their answers, which again are exponentially long, we verify whether this formula defined by F is satisfiable or not. So as we said last time, everything here is exponential. The length of questions is exponential. The time complexity of sending the questions is exponential. The answer length is exponential, and also the processing, the post-processing time is also exponential. And the way we are going to handle this big protocol is by somehow, in a magic way, reduce the size of the questions to polynomial. So we took this thing and we said we want to reduce it to polynomial. And by that, also reducing the processing time to a polynomial. And afterwards, we will do it in 2 steps. We will take these things and reduce them to polynomial.
Michael, can you just please show the bullets of the big protocol again? Or
yeah,
maybe the slides are available?
You start by some instance of succinct 3-sat.
Okay.
You calculate what Boolean formula it defines. It defines some exponentially large Boolean formula. Then from this Boolean formula, you generate, as Guy did, this game G of F, which is a 2-player, 1-round game with soundness, completeness gap of 1/2, okay? And you play this game with the players, and by that you verify whether if this game has value 1, this formula is satisfiable, and if this game has value at most 1/2, this formula is unsatisfiable.
Thanks.
Great. Notice that the only difference between this case and Guy's case was that instead of getting F as an input, I am getting F in a very succinct, compact way. This is the difference. So I am getting the same F, but now it is represented by a much shorter circuit. Thus, it is exponentially large with respect to the input that I've got. Okay.
Michael, can you go, sorry, I'm bringing you back in this dance. So basically, can you go just a little bit more down? Okay.
More down?
So, yeah, like this. So so this big protocol, if you don't make the question length polynomial instead of exponential, then this shows that NEEXP, NEEXP, right? That NEEXP is in MIP, but not MIP, but MIP with exponential questions, exponential answers, exponential time, everything. I don't know.
Yeah, so I wrote it here. Yeah, this is correct, and this is automatic from Guy's work.
Right. So this is automatic, and then the effort that you're now making is to show that you can reduce from exponential to polynomial everything, and this is where you need quantum even for the honest prover, even for completeness.
Yeah, you're correct. So non-quantum prover could not win the game that we are going to play at the end. So we are not going to generate some game G of C, which is dependent on this circuit C. And to win this game with probability 1, you need to use entangled particles between the two provers. So
yeah, but only when you make the exponent polynomial.
yes,
They replace the exponential with polynomial.
yes, exactly. Yeah, for at least for now, we don't need any entanglement for what you, as you said, the NEEXP is contained in MIP EXP. You don't need any entanglement, but the way we are going to, the fact that we can reduce it to NEEXP is contained in MIP star, it is actually MIP star. We cannot, it cannot be done, even the completeness part cannot be done by non-entangled provers. Right, this is a good point. More questions, remarks that you think there should be? Okay, thanks. So I'm going to do I had this, I wanted to present at the end of last time. Actually, I thought it won't be the end, but at the end, this thing that I call the super Pauli basis test. But after a chat with Guy, Nati, and Dorit, I understood that maybe we should give a bit broader context of what is, again, an X measurement and a Z measurement on a qubit. And only after I'll do that, and I'll try to do it on the one hand briefly, but on the other hand, in a way that everyone understands. So please, those of you who are less familiar with this concept, please stop me whenever something is not understood. And then when we actually understand what is the deal with these X and Z measurements, we will talk about the super Pauli basis test. And then I will explain how this super Pauli basis test enables you to reduce the question lengths in our test. Okay, so let me zoom out a bit. Okay, so we have a state psi. Okay, so we always say that we have some psi that sits inside, for example, only C squared. Okay, so I'm showing you R squared, but this psi can live also in C squared. And there are two bases inside C squared. The first basis is called the Z basis, which is just the natural basis with respect to the axis. This is 1, 0, and this is 0, 1. This is the Z basis. And we have also this is in red here. And we have also the green basis, which I call the X basis, which is just 1, 1 normalized and minus 1, 1 normalized. Okay, so these are the two bases. And when I'm saying that I'm conducting a Z measurement, I'm doing the following. I'm doing one of the following two actions. I'm either projecting this psi onto Z1, and the probability, okay, so the probability is Z measurement, okay? Okay, so when I'm conducting a Z measurement, the probability that outcome is a projection on Z1 of psi is the size of the projection, okay? So pi Z1 psi, it's norm square. Okay, so this is some number. We have this length here. This is the norm of the projection. I'm taking this norm squared, and this is the probability. This is a number between 0 and 1, this norm squared, because psi was a unit vector. This is unit vector. This is the probability that the outcome will be the projection on Z1. And in this case, I'm saying if this was the outcome, the player answers with +1. You see, I called this vector, this basis vector Z1. So when this is the outcome, the answer of the player is 1. Okay, so the answer will be either +1 or -1. And the other probability, so the probability that the outcome is the projection on z minus 1 of psi. So this is the other possible outcome. And this is equal to the, it's the complement, but it's again just the size of the projection on the z minus 1 axis of this state psi squared. So this is my formula. This is the way I think about measurements. Okay, so we have this length, you take it squared, and this is the probability that you actually answer with the -1. Okay, so for the x's, we have the same thing, but they are oriented 45 degrees, I don't know, anti-clockwise. Okay, so again, you want to ask yourself, what is the probability that if I'm measuring an x measurement, what is the probability, and the state is psi, the probability that the answer will be 1 is exactly taking this projection and taking the square of it, and this is the probability that the player will answer 1 if the player measures with respect to the x basis. And similarly, if the probability that it will answer, that the player will answer -1 is that this projection squared. Okay, so we see geometrically that measuring with respect to a z basis gives me a different, like different probabilities of answering 1 and -1 than measuring with an x basis, potentially, okay? Any questions up till now about this point? No, great. Okay, so this should have been maybe clarified earlier. I talked about it only a bit. Now we have inside now, okay, so now I'm thinking of 2 qubits. So we have c squared tensor with c squared. And in this space, this is a 4-dimensional vector space over the complex numbers. There is a very special state, a very special psi that we call the EPR pair. And yes, Guy?
Yes. It seems to me that you're making a jump here because you're talking, okay, it's not a jump, but just one comment, which is that there's more than one way to represent a measurement. One is according to a basis, and that's more or less what you did here. And another is via an operator. And then it's really just a measurement with respect to the basis of eigenvectors of the operator.
Yeah, okay, so from this representation of a measurement, I could generate an operator, and the eigenvalues of the operators are defined using the outcomes that I chose here. So my point is that you can take the projection on Z1 and take it with a coefficient, which is the eigenvector, the eigenvalue that I want to represent, which is 1. And I'm taking plus the eigenvalue that I want to relate to the other projection, Z minus 1. And this generates an operator. You can check that this is just the matrix 1, 0, 0, minus 1. Okay, with respect to the standard basis. And this was the matrix that I called Z all the time. I called this matrix the Z matrix exactly because what a guy just said, that you can think of the measurement as projecting onto the eigenspaces of some operator. And in this case, it's projecting on the eigenspaces of this operator, of this Z operator. And similarly, you can check that if you take the projection onto x1 with coefficient 1, and you take plus minus 1 times the projection onto x minus 1, this is just the matrix 0, 1, 1, 0. Okay, so this is an easy check. This is just a calculation. So this one I called the X matrix, the X matrix. So again, as Guy said, these are two ways of representing the same idea. And when I'm saying you measure according to the X operator, I mean exactly projecting either onto the X1 axis or onto the X-1 axis and answering accordingly, either a 1 or a -1 with the corresponding probabilities. Great. So another thing is that, okay, so now I'm talking about the EPR pair. So the EPR pair is just this vector inside C² tensor C². But since I'm using the Kronecker product, this is just this specific vector in 4-dimensional complex plane. It's just 1 over square root of 2, 0, 0, 1 over square root of 2. You can think of just this vector. And now I want to say, what does it mean? Now we have Alice's side. So this is a 2-qubit system. It's a system with 2 particles that can fall onto 2 states. It can fall into, when you measure according to some basis, you call one of the bases the 1, the other basis the -1, the other basis element the -1, and then you answer accordingly. So there are only 2 outcomes. So we think here of 2 qubits, and we think of the left part as Alice's part and the right part as Bob's part, and so on. Now let's check what is the probability, what happens when Alice measures with respect to the operator Z tensor I. When I'm saying that, I mean that Bob is doing nothing and Alice is taking her part of the qubits, of the 2 qubits, and measuring according to the basis that, the red basis that is on the board, that is still observable in the board. So the claim is that the outcome is either projecting the vector EPR, the EPR pair, onto, I want to take another color, okay. So onto this space, the tensor product of 1, 0 with C², which is just the span of these 2 vectors. Or the other outcome is that the EPR pair is projected onto this subspace, which is just the span of these 2 vectors. Maybe I'll zoom in back. Okay, so these are the 2 possible when A measures with this operator, meaning it just checks the Z measurement on her particle. It just means that it projects the outcome on either of these 2 subspaces. Why is this not fixed? Okay, great. Now we need to check that it means that it takes this vector and it projects either here or here, right? And you can check that it means that it either kills the last coordinate, and the probability of that is 1, and or it kills the first coordinate, and then, sorry, the probability of that is 1/2, and or it kills the first coordinate, and the probability of that is still 1/2. And in the first case, Alice answers with a +1, and in the second case, Alice answers with a -1. This is exactly what it means that Alice measures according to the Z basis. And this is the calculation, this is the mathematics behind it. Guy, you want to remark something?
Yeah, just to comment, yeah, so these 2 spaces, the 2 spans are just the eigenspaces of this operator Z.
Yeah, so back to the representing Z, the measurement using an operator, you can check what is the eigenspaces of Z tensor I. The 1 eigenspace is the first one, and the -1 eigenspace is the second one. And exactly, Alice answers according to the eigenspace it projects on.
Yeah, and my second comment is, in principle, to check the probability of each outcome, you need to calculate the norm of the projection of...
Yeah, I did that.
But
yeah,
here...
it's 1 over square root of 2 squared.
Yeah, here you don't really need to. It's obvious that the 2 projections are, have the same norm.
Correlation, yeah.
No, it's the
Yeah,
same.
okay. So in this case, it's clear, but in general, you would need to do all the calculations. The probability you get here is 1/2. You can either see it intuitively or you can just calculate I think it lives in the span, our vector lives in the span of this vector and this vector, and it is exactly with equal coefficients with respect to these vectors. So yeah, clearly the projections, which is the inner product, is equal, right? So okay, in this case, it's easy. The fact that it's probability 1/2. Maybe it's a bit more difficult with respect to other bases, but in this case, it's easy. Now let's ask ourselves, if after, the point is that after Alice measured her part of the particle, what happened if Bob measures with respect to the same basis, with respect to Z? Okay, so again, when Bob measures with respect to this I tensor Z measurement, he projects onto either this space or this space. And again, this is an easy check by definition. What does it mean to project on the span of 1, 0 with everything else? It means projecting on the span of this thing. And what is spanning on 0, 1 tensor everything? It's just projecting on this thing. And the point is that if Alice answered with a 1, now the state is not the original EPR pair. The state is just 1, 0, 0, 0. So on which space does Bob where does Bob going to project the current state?
Zero, 1, 0, 0.
Why? You look at these spans. Our current state is this thing. It's 1, 0, 0, 0. It lives inside one of these subspaces.
Can.
So it's going to project.
The reason I'm laughing is I didn't know I was muted, but the reason I'm laughing is because for some reason I don't understand why, but this is difficult, even though it's extremely basic. And after 20 years of trying to explain it, I still think it's difficult.
Yes.
Same.
Yeah, I didn't mean to make you
describe the sequence
like this is easy, but I want you to feel that you understand the mathematics, even if this is not easy. The point is that now we have a vector 1, 0, 0, 0, and we need to project it either to the first space here that I'm going to call Z Bob 1 or into Z Bob -1. And the point is that the probability of either outcome is relative to the size of the projection on either of the spaces. But this
it's in the first space, right?
This state is perpendicular to ZB-1 and lives totally inside ZB1. This just means that in the way we thought of measurements as projecting, it will, with 100% probability, project onto ZB1. But this means that Bob will surely answer with a +1. Mm-hmm. And if the outcome of Alice's measurement was the other vector, the 0, 0, 0, 1, clearly Bob will just project onto ZB-1. And this means that Bob will answer with a -1. So the point is that if they share the EPR pair and both of them use the same measurement, the same Z measurement, and similarly you can check with the X measurement, this is the same, they are completely correlated. This is the point. With 100%, they will answer the same answer. Okay, so this is an important point. Please ask questions now. I think this is...
Catch to ask, you know, it's not even mathematics, it's cheshbon.
Yeah, okay, so this
the argument is so elementary. No, it's very surprising when you tell it in the beginning, but when you see what's under the hood, there is nothing.
Right, you're right. So this is basically linear algebra. But let's see.
Not even, you know, it's.
Yeah, but let's see what happens when Bob is measuring with respect to the other basis. And I chose the other basis to be 45 degrees oriented with respect to the first, exactly because I want the following behavior to appear. Okay, so let's see what happens here. Okay, now if the outcome, okay, so the point is that Bob either projects onto this space. Now this is called X Bob plus 1, and this is X Bob minus 1. These are two subspaces, and measuring with respect to the X spaces means that you either project onto X Bob plus 1 or onto X Bob minus 1. But let's check what is the probability of getting either of these things. Now, notice that if Alice got as a result 1, 0, 0, 0, it's exactly equal to 1/2 times 1, 0, 1, 0 minus 1/2 minus 1, 0, 1, 0. So this
write it down instead of having us remember one.
It's on the board.
It's on the board.
What?
It's on the board. I will highlight what I'm
okay, yeah. Okay, sorry. It's
1, 0, 0, 0 is equal to 1/2 times 1, 0, 1, 0 minus 1/2 times minus 1, 0, 1, 0. So again, the coefficient coming from X Bob 1 and the coefficient coming from X Bob minus 1 have equal size. So the projection on either spaces is of the same length, meaning the probability of getting +1 or -1 is 50%.
They are equally likely.
Yeah, they are equally likely. Thanks. And you can check, I've done the calculation also for the 0, 0, 0, 1. It's equal to 1/2 0, 1, 0, 1 plus 1/2 0 minus 1, 0, 1. So again, Bob will answer with 50% with equal probability +1 or -1. So what you should take from it is that as opposed to the first case, in this case, they are completely uncorrelated. So Alice and Bob there is no connection between the result of Alice and the result of Bob. It is as if they flipped two coins on their sides, and you can say nothing about one coin by checking the other coin and so on. Any questions about this point? Okay, so this was a short introduction to all these X and Z measurements. And now I want to go back to the magic square game because I think this point was not understood well enough last time, and it is important to understand the following point. So let's call the magic square game. What?
Yeah, so just, okay, never mind, just continue.
So we had just to repeat what you said. If they measure with respect to the same basis, then they'll get the same result. If they measure with respect to distinct bases, then they're completely uncorrelated.
Exactly, and this is very dependent on the state, this magic state called the EPR pair, okay? Like, this is not a general phenomenon.
Sure.
This is just a specific phenomenon related to the EPR pair.
It's also not for a distinct basis. It's not that any basis, if you change it by a little bit.
These particular two bases and this particular state have this.
Yeah, these particular bases, as long as they're 45
sure.
related, degree related to each other.
That's what we needed, yeah.
Yeah, exactly. Okay, so let's recall the magic square game. So now I changed the names that I used last time because people said that they were a bit confusing. So now I have one player which is called the constraint player, and one player that is called the variable player. So I'm sending to the constraint player either of the following. So I can send him row 1, row 2, row 3, or column 1, column 2, column 3. So the constraint player have 6 possible questions. The variable player gets one of the squares inside the 3x3 grid. Okay, so I can send to the variable player x1, 3, and I can send to the constraint player column 3. Okay, this is a kind of pair. These are two possible questions to the players in this game. And what do I expect them to answer? So the variable player needs to give me one output, either a plus or minus one. And the constraint player needs to give me three outputs. It needs to give me plus minus one, comma plus minus one, comma plus minus one. And I think of it as the following. So saying, for example, so the orange will be an example. Say that the variable player answered with a plus one and the question was x13. It means that the variable player answers with plus one on this square. And the constraint player, maybe he answered minus one, minus one, minus one, and then I'm writing here minus one, minus one, minus one. And what am I checking? I am checking that the constraint is satisfied. And the constraint is the following. The product of every column should be minus one, and the product of every row should be plus one. So you see the constraint here is satisfied. Okay? And the second thing that I'm checking, okay, so for the constraint is satisfied. And the second thing I'm checking is that the value that the constraint player gave to this square is the same as what the variable player gave me. And in this case, this is not true. They gave me different values. Thus, they lost this round. But if the variable player would have sent me a minus one, they would have won this round. Any questions about this game up till now? Okay, great. So Dorit said last time that there is a variant of this game, and I want to remind you what this other variant of the game, where one player is the row player. You send the player A either row 1, row 2, or row 3, and you send to the other player either column 1, column 2, or column 3, and you check the same thing. You check that the rows are satisfied, so the row player needs to give you 3 numbers whose product is plus 1. The column player needs to give you 3 numbers whose product is minus 1, and they have an intersection variable. This intersection variable should be consistent. Yeah, thanks.
That's how the kids in Haifa played.
Yeah. So for the Haifa, this is the variant. And I want to say something about this variant because there is some point in the proof of MIP star is equal to RE, and also in this NEEXP thingy, that this variant is not good for us. And I will explain where. It will probably come either today or the beginning of next time. Okay, so this is the Magic Square game. And last time I just wrote you a perfect strategy. My claim was that there is a perfect strategy, meaning a way of defining a Hilbert space for Alice and a Hilbert space for Bob, choosing a unit vector inside the tensor product of these Hilbert spaces, and choosing measurements, actually projective measurements, onto subspaces in these Hilbert spaces, such that they win perfectly this game. So let's recall what is the perfect strategy. So I need that Alice's Hilbert space consists of 2 qubits, okay? So it's C squared tensor C squared, and I'm calling the first qubit C squared A1, and the second qubit 6 squared of A2. And also on Bob's side, there are also 2 qubits. So there is C squared of B1, tensor C squared of B2. So in total, our space is 16-dimensional and consists of 4 particles. And the point is that I'm now taking, an EPR pair that is consisted out of these 2 copies. These 2 qubits generate an EPR pair. And also these 2 qubits generate an EPR pair. And the EPR pairs are uncorrelated with one another. Okay, so the first EPR pair is uncorrelated with the other EPR pair. So here you see I have one EPR pair that consists of the first registers of Alice and Bob, and it is just tensored. Being tensored means it is uncorrelated with the other copy of an EPR pair. But again, you can just think of this vector as some vector in a 16-dimensional space over the complex numbers. And now I'm showing you a picture of what the C player is doing. The C player is not the constraint player. It's either Alice or Bob. Okay, so the point is that the strategy of Alice is the same as the strategy of Bob. Whenever I'm either, it doesn't matter whether
are we playing now the Haifa game or the row column game?
Actually, this strategy is good for both.
Okay.
Yeah, but you will see that we need to do something bad when we need to do the Haifa version. And I'll explain bevor עת why. In times being?
In due time.
In due time.
Due course, yeah.
Okay. Okay, so what is the point? Now every player has 2 qubits. How do I answer this square? I am measuring my left qubit with respect to the x basis. This is on my side. This is on, for example, this is Alice's side. Okay? She has 2 qubits. One of them is entangled with one of Bob's qubits. The other is entangled with the other qubit of Bob. And now Alice is just measuring the first one, what I'm calling the first qubit, the one coming from C squared A1. She measures it with respect to the X1, to the X basis, and I'm calling it X1. This is the same as acting with the operator X1 tensor I2, only on Alice's side. So actually it's the actual measurement here is X1 tensor I2, tensor I1 coming from Bob's side, tensor I2 coming from Bob's side, meaning Alice can do nothing to Bob's side. And this is clear, right? She's only measuring things on her side of the world. Okay, she's measuring the first qubit with respect to the X basis. Now, if she wants to answer this question, she needs to measure her second qubit with respect to the X basis. Okay? Now, if she wanted to answer this question, she needs to answer with respect to the Z basis only on her second qubit. She does nothing to the first qubit, but she is doing something to her second qubit. She measures it with respect to the Z basis. Now, there are interesting measurements here. This measurement, so I'm going to take another color. This measurement has a different flavor. It is asking the following question, okay? So the measurement that is related to this point of the square is the following. If I would have measured both my left qubit and my right qubit with respect to the X basis, would I get the same answer? If the answer is yes, the answer is +1 in this square. If the answer is no, I will write a -1 in this square. So this is a bit more complicated. I don't know whether this is correct to say. This is a bit more complicated.
It's a qubit more complicated.
Yeah, qubit more complicated. Thanks, Nati. Measurement. But it is still something like you can take the matrix, which is the tensor product of 0, 1, 0, 1 with, 0, 1, 1, 0. You can take the 0, 1, 1, 0, 0, 1, 1, 0 tensor product. It has some eigenspace with respect to +1. It has some eigenspace with respect to -1. And you will answer +1 if you projected on this eigenspace, and you answer -1 if you projected on the other eigenspace. So even though this measurement is a bit more complicated when you try to explain what it does in the physical world, in the mathematical sense, this is just the same. You have two eigenspaces. One of them is correlated with the eigenvalue 1. The other is correlated with the eigenvalue -1. And you project onto either with respect to the length of the projection on either space of our state. Okay, great. So these are the kinds of measurements. And so this is an even more complicated measurement. And this is maybe the most complicated measurement in all of this square, but still you can just think of the operators and check what are the operators and define projections on these operators. Okay, so now what happens? If Alice asked for the first...
This is, I mean, but from the, I mean, I think you explained really well how, what the measurements do. And now, just to check the technicalities, if you take the product along the rows, you get a plus. And if you check the plus I,
yeah,
plus, okay. And if you multiply along the columns, you get a -1 as needed, right?
Yeah, you get the operator plus I if you take the product of the rows, and you get the operator -I if you product the columns. Yeah, this is true.
And so in principle, you could have simply, you could, I mean, it's very good that you've done it this way, but it's, you can just now multiply the matrices and check that this is what happens, right? That these are the properties. So
yeah,
I don't know, for example,
you need
the fact that any strategy that wins with 100% probability actually comes from an operator solution is true.
No, I'm not claiming anything like this, Michael. No. All I'm saying is if you take the product along the first column.
Yeah, but what is the relation between taking the product and actually winning the game? This is not clear. So you should check that actually if the product, it means that actually if the product is I, no matter, now the eigenspace of 1, okay, so with respect to what Nati said, if I want to measure all of these things, it's the same as multiplying all these matrices, actually. And okay, so the product of my answers will be just the same as measuring with respect to the product of the matrices. The fact that the eigenspace of I is either 1 with, like the whole space is the eigenspace of 1, and then there is no eigenspace of -1. This means that actually the product of the answers will surely be 1. This is correct. And this is the relationship between the fact that the product of the operators is the identity, and the fact that they will, if they measure according to this thing, actually, no matter what the state was, if they measure according to these measurements, they will satisfy all the constraints, at least the constraints. They not necessarily will be consistent, but they will satisfy all constraints. Yeah, Guy.
There is one thing which is more basic and should be said even before Nati's point, and that is that every row and every column has commuting operators.
Yeah, this is also true. So
and that is important because the fact that the operators in each row and column are commuting means that they have a joint, a common eigenspace. They have common eigenspaces.
Right.
And that means that basically once you measure, so there is a common basis of eigenspaces, and although it looks like you do 3 measurements to get 3 different answers, you could have just measured according to these bases, and then you would get 1 vector, and this vector is a 1 eigenvector of the first measurement and a -1 vector of the second measurement, or whatever. The point is that the measurements do not affect each other. Once you project to a space by doing 1 measure, you remain in this space by doing the other measures because they share the eigenspaces.
Yeah, that's a good point.
So there is a meaning to ask if I apply all these measures on a vector, what there is a meaning to asking, like,
there is a meaning to asking what is the eigenvalue of each one of these operators separately, together.
Right. Yeah. So.
Okay, so it is an important point, but I think the mathematics here is now understood, at least after Guy's remark, and I want to say a small thing before we take a break. We'll take a 10 minutes break, and this is that this is a robust self-test. And what is a robust self-test? It means that there is only one perfect strategy, and almost perfect strategies are close to this strategy in some metric. And actually, in this case, the metric is what we call the normalized Hilbert-Schmidt metric. So if you take a Hilbert space for Alice and a Hilbert space for Bob, and you know that the strategy, there is some psi in this space, and there are these measurements, okay? So there's M11, M12, M13, and these are the measurements that they use for the brackets in this 3x3 grid. Then M11, after some isometry, so I'm applying some isometry to this space. Maybe I'm embedding it in some larger tensor product of Hilbert spaces, but after some isometry that I'm calling phi, actually M11 minus X1 tensor I2 tensor some maybe IK, you need to maybe take the tensor with some identity, I don't care. The difference between this thing in the Hilbert-Schmidt, the normalized Hilbert-Schmidt norm, is bounded by the success probabilities. So if this is 1 minus epsilon success, this is bounded by some function of epsilon, which tends to 0 with epsilon. Okay, so this is what it means to be the fact that this is a robust self-test. And clearly the psi, again, after isometry, phi of psi is minus the EPR per EPR tensor EPR, which is the state. This is EPR1 tensor EPR2 that I remarked here. Maybe tensor some auxiliary and that I don't care about.
The yellow is not so well visible. Can you do different color? I mean, it's visible, but not too.
I'll do it in black. Okay. I'll do it in black anyway. So the point is that after isometry, the state is very close to EPR. EPR1 tensor EPR2 tensor some rubbish. And the point is that the MIs, the MIJs do nothing. They don't measure the rubbish. They actually, okay, so they almost do nothing to the rubbish in some sense, okay, because they are only close to the things. The fact that I took here IK means that actually the MIJs almost do nothing to the auxiliary part. Okay, anyway, this is the kind of stability result that is needed in the games industry. And the Magic Square game has this property. And my claim is that the only thing you need to know is the representations of the 2-qubit Pauli group, or otherwise the dihedral group with 8 elements product with the dihedral group with 8 elements. Like, this is the only information you need to know for mathematics to prove that this game is robust. Okay, so let's take a 10 minutes break.
Coffee time.
Huh?
Coffee time.
Yeah. Sorry for prolonging.
Don't force people to get coffee. I was always afraid where people said, let's get coffee, that I will have to drink coffee.
אתה לא חייב, גיא.
תודה.
זה כמו אנשים בהפגנות שאומרים, אל תכריחו אותנו לקבל חיסונים. בינתיים אני רק רואה שאנשים כמעט הורגים אחד את השני בשביל לקבל חיסונים.
כן, זה לא אותם אנשים.
כנראה שלא, אבל אני לא יודע אם הם שותים קפה מצד שני.
Question? Can I ask a question?
Yeah. Thank you.
The
I'm
MIP
here.
star, it's about having there.
You were very,
Can you hear me?
like I didn't hear you well. Your internet was a bit problematic.
Yeah, unfortunately today my internet is slow. So MIP star, it's about having a polytime verifier.
Right.
We can define something like MIP star, but where the verifier has arbitrarily large computational power, let's say.
Yes, but
The
we
class-
now know that this, at least there is no, you don't gain anything by
The
moving
class-
from polynomial to exponential.
The class will still be equal to Ri.
RE, yeah.
RE, okay. My question is, because for us mathematicians, for the information of cone embedding problem, this result will be enough. Can we have an easier proof in this case? Because we are not interested that much in the polytime of the verifier.
Sorry,
No,
which result would be enough for the cone embedding conjecture?
Yes, so to be enough for the cone embedding conjecture.
Which result will be enough?
If instead of using polytime verifier, we use arbitrary large computational power for the verifier.
but still fixed.
Not necessarily.
No,
Okay, so
not-
this would not be enough. No, this is not true. This shouldn't be enough because otherwise you cannot distinguish between. Okay, so the way that Cyrilson's problem is related to
if you
this.
don't restrict the verifier at all, then he can do RE
Yeah, exactly.
without using anything, without even
No,
conversing.
but he has to say if a Turing machine does not stop. He has to still say that. He will still have to stop on answering that, no, this Turing machine does not stop. I don't care how much time it takes, but at the end of the day, he'll have to stop.
Okay. Maybe you are right. I'm not sure. I'm not sure about it. Like, this is a good question. Maybe I'll ask Thomas about it, and then this is interesting. Okay. Okay, so usually the way I think of it is that you have this, for any game, you ask whether you can calculate its quantum value, right?
Approximate, okay.
Approximate its quantum value. And there is an algorithm that approximates the quantum value from below. And there exists this algorithm that approximates the quantum commuting value from above. And
but I still have to understand. I couldn't read that article at all.
What?
I had
What
difficulties.
happens?
Wait, Alon, wait. Alon. And the point is that if the quantum value and the quantum commuting value were the same, meaning Cyrilson's problem was correct, this algorithm would have stopped at some point and say,
it can distinguish between a situation where the quantum value is 1 or less than 1/2.
Yes, exactly.
And then there will be a Turing machine.
They know that this is the halting problem is in this set of questions, and thus there is no algorithm that can verify this thing. So where does the
so the values cannot be equal. The tensor product and the commuting product cannot be equal for all games.
Yeah, but the model is that the game, the definition of what does it mean to win a game is when the verifier has some how do you say, what is the value of a game? The value of a game is what is the probability of them winning under some restrictions on the verifier, right? Like this is part of the definition of what is the value of a game. You're defining now a new thing called the a Superman value game where the verifier has no limits on its computation time. Maybe it is true that also that this is enough to prove Cohn's embedding, but I'm not sure that this is true. Like, I don't see that, like, maybe the values behave very differently when you add this, like when you loosen this restriction. Right?
But the class still should be equal to Ri.
No, the class is equal to RE because of what Guy said. The fact that the verifier is unbounded automatically means that it can verify any problem. No, it can answer any problem in RE, but this means that it will not say that any Turing machine halts or doesn't halt. It just will say when something halts and will not say anything when something doesn't halt.
The verifier just produces a game, no? This is how I...
No, the verifier is part of the game.
Yes, sorry.
Right? You want to say whether there is an algorithm that for a specific game tells you whether it stops or not, but this algorithm needs to terminate in some finite time. And you don't care about the length of this time. So in some sense, you have something which is which has no conditions on it. The algorithm runtime that needs to tell you, given a game, what is its value, this thing is has unbounded computational complexity.
Mm-hmm.
Can I say something? Maybe as far as I understand Pilviu's question. I mean, once you assume Tzielson, you have a polynomial time algorithm of deciding a game's quantum value, right? This is no, like it will always be polynomial. You have a semi-definite program approximating from above, and from below you just do something. But
why
I
is
think
polynomial alone? No, you have no bound.
Please.
You can show that there is no bound on this algorithm of approximating, even before you are saying something about Tzielson's problem, whether it's solvable or not. The fact that this will never be polynomial, even if Tzielson's problem were true, this wouldn't be polynomial. This is not true.
Wait,
even if the game is very compact, maybe the strategy needed to win this game lives in a very, very, very large dimension, needs many entangled qubits. Okay, so doubly, triply, exponentially many entangled qubits. So this fact is not true. It will terminate, this is true, but you have no bound on the time complexity of this algorithm.
You are referring to the one by Stark. I don't remember what are the names. I think it is the one approximating from above the quantum commuting value. It is not polynomial.
What does it mean? You can never approximate the quantum commuting value. This is part
from
of
above.
But
from above, not from below.
What does it mean from above? And what does it mean polynomial? I'm giving you a game. Okay? I'm asking, can you approximate the quantum value up to 1/3 from above? The quantum commuting value of this game by 1/3 from above. You will never know when to stop.
Okay, okay, sorry.
So the fact that you cannot calculate the value of the game. Okay, this was a bit of a side thing, so maybe let's resume this discussion at the end and not now, because I think it's interesting, but not. It's not relevant in a straightforward way to what I want to talk about today.
Yeah.
Okay, so I'll disconnect my iPad and reconnect it as usual. Great.
Michael, I don't want to start a discussion now, but I must say I still don't understand how this model allows you to compute uncomputable things. I mean, what are the implications of this? This I don't understand yet. It's very basic.
If there were if there were two gods that you could have control and separate spatially, and these two gods both know for any Turing machine whether it halts or not, and they can share unboundedly many entangled qubits before you separate them. They can...
You can become God yourself.
No, okay, so what does it mean, God, in this scenario? It means that if you are given a Turing machine, you can decide whether it halts or not only in polynomial time with respect to the input Turing machine. So the Turing machine has some size, the description of the Turing machine.
I understand. You explain it very well. Yeah. It provides new meanings to לא יהיה לך אלוהים אחרים על פניי. Now I finally understand the issue, yeah. The two of us, who knows, the world would go into chaos.
Yeah, so it would be too strong to have two gods. Okay, so let's move along. I'm sorry, those of you who are with me, that's good. So we saw this magic square game. And my point was, if the players want to succeed in this game, they need to, when I ask the variable player for the upper left corner, he must do nothing to okay, so the doing nothing is not important. Okay, so the fact that he does nothing to the other point is not important now. Maybe he does something, maybe he does other measurements, but he doesn't use the variable player when measuring this square, measures the left qubit that it has with respect to the x basis, and we can assume that it does nothing to the other qubit because it cannot affect the outcome. Okay, so at least with respect to what he answers, the answer of this player does not depend in any way on the right qubit. Okay, so in some sense, I force, when I ask the variable player for this square, I force the variable player to measure his left qubit according to x and do nothing to the right qubit.
I'm sorry, Michael, we are now starting to talk about stability. Is that what we're doing now?
No, the fact that this is a self-test, I mentioned that there is only one perfect strategy. So for the player to win with perfect completeness, okay, with probability 1, when I'm asking the variable player for this specific coordinate, for this specific bracket inside this 3x3 grid, the player must do a specific measurement on a specific qubit. You agree with me, Nati? And when I'm asking him to measure this thing, he must do a z measurement on this qubit. Okay, so I want to give you a way. We said that to reduce questions, we need to explain how to sample a point and sample a line. So I'm going to do a first try, which is a bad try. Okay, so I'm a priori saying that this will be not a good way of sampling a point and a line. But I'm constructing now a game. Using the magic square game, I'm constructing now a game. The game is the following. We play MT. Okay, so I want to try to make them share a point and a line in F2 to the T to the M.
So, Michael, you jumped. I didn't understand your jump. What are you now trying to claim? Like, what's the claim now?
There is no claim. I want to define a game. But the goal of the game is the following. If they want to win with perfect completeness, they need, I will force them to sample a point and sample a line. Okay? So I'm going to generate a game that for perfectly playing provers, they must sample a point and sample a line if they want to win with high probability, not with high probability, with perfect completeness in this game. So I'm ignoring the soundness thingy. I'm only talking about the perfect completeness.
Sorry, Michal, can we go back? You're going to use the robustness, or not the robustness, the uniqueness of the strategy of the Magic Square game. So yeah. Can we just say for a moment the claim about the uniqueness of the Magic Square game strategy? So what you're saying is that if two players share a quantum state, no matter what, and if they have some strategy, which for the game, the Magic Square game, says that for any input, player A measures according to some operator, player B measures according to some operator. That's a strategy, right? This description of what they measure by and what would be their answer by this measurement.
Yes.
If they succeed with a Magic Square with probability 1, then their measurements are exactly that, up to localizometry, meaning up to rotation on A by some matrix and on B by the dagger matrix.
Yeah, you're correct. This is exactly what I'm saying.
Okay. And the claim about the identity somehow,
yeah,
I don't know.
I don't want to say anything more about the identity. The point is that the variable player doesn't use any measurement on the second coordinate to decide what is the answer to this square. Okay? You agree with that, Dorit? The fact that
let's not go into it. It will drag. It will take the discussion to some unwanted place. Yeah, I more or less agree.
Okay. Great. So I want to define the following.
Well, I'm sorry, I know less, so I can probably do less damage. But isn't the claim that you want stronger, that this is essentially their one and only strategy with no assumptions on what they do?
Yeah, there's no.
The only strategy up to isometry, Nati. They always have.
Sure. Okay, that I understood. That's nothing. But
this is what Dorit said.
Okay.
Yeah.
There is a single perfect strategy, and the fact that one of them does nothing to the other coordinate is important at some point, but at least for now, we can ignore it. Okay. Okay. So now I want to generate a game again, which is a bad game that actually forces the players to sample a point and sample a line in F2 in this vector space. Okay. So what am I going to do? I'm going to parallel. I'm going to play empty parallel magic squares, magic square games. Okay, so when I am playing empty parallel magic square games, I know that the players must, for them to win with perfect, again, only perfect completeness, I'm not talking about the stability result. For them to win with 100% probability, they need to share how many, let's calculate together. Okay, so for any game, they share 2 EPR pairs, right? So they share 2 times M times T EPR pairs. Do you agree with that? Great. So maybe I want to play even two empty parallel magic square games, and I'll explain in a moment why. So I want 4 empty EPR pairs. And the point is that when I'm asking, and now let's say this is even shooting myself on the feet, how do you say it? Because I want only one player to be the variable player in all of these parallel games, and the other player to be the constraint player in all of these parallel games, okay? And now I want somehow to use the self-testing of the Magic Square game to force them to sample a point, for example. So now Bob has 4 empty qubits. And the point that is that I can tell Bob sample point. And what Bob needs to do, the honest Bob needs to take the empty qubits out of his qubits, okay? So he takes empty qubits and measures them according to Z. Now, how can I verify that Bob is actually doing this thing? The way I'm going to verify that is that I'm going to send Alice the variables that force Alice to measure qubits according to her Z basis. Okay, so I'm going to send Alice, I don't know, empty questions of this form. Okay, so in the first empty square games, I'm going to send Alice this variable. Now Alice doesn't know that she plays, she doesn't know whether she plays against the 2 empty Magic Square games. Okay, potentially now she is playing the Magic Square game, but now I'm adding the complication, I don't know how to say it, that maybe Alice is now playing against sample point Bob. And the only thing that they need to do is be consistent. So the sample point Bob needs to output a string of bits, which is the same string of bits that Alice is using in the Magic Square game. But for him to do that, he must use the EPR pairs that he constructed for the Magic Square game and apply the Z measurement on these qubits. Otherwise, he will not win this mini game. Okay, so this is a graph of mini games. You either play these 2 empty parallel Magic Square games, or you take the variable player and משווה אותו? Compares him with a new game, a new mini game that's called sample point. And in this way, I can verify that when I'm telling Bob to sample a point, he must do it in this specific way. He must take his first empty EPR pairs and measure each of them according to the Z basis. Was that clear? Okay. Maybe.
Sorry, sampling a point is here just giving sampling a string of empty bits.
Okay, so it's not okay. So this is a mini game, okay, Dorit? So now I'm sending to Alice a question that looks the same as 2 empty parallel Magic Square games. I'm sending her.
Can you go to Kita Aleph? Just yes. What does it mean to sample a point? What is the if everybody is honest?
I haven't got to this. Like it will come in a moment. The thing is that I want Bob to be consistent with the first empty measurements of Alice. Okay. Up till now, this is the only thing I wanted him to do. And for that, he needs to measure empty qubits according to the Z measurement. Otherwise, he will not be consistent with Alice. Was that clear? Now I'm going to add, why was not that was, why was?
I don't understand where you're going. So it all looks like a big cycle.
Okay.
Don't stop me. Please don't stop me. I will try to explain what I'm trying to do. Bob gets a new question. Now we have a new game. There is you either play two empty parallel magic square games, or you compare answers from the variable player of the two empty parallel magic square games against some new games. So one of the players just gets, as usual, variable, and then a sequence of squares inside the magic square game that he needs to answer. Okay, so in this case, it's Alice. So Alice needs to, again, win the magic square game, and she gets a list of variables she needs to measure, right? Like in the square. Mm-hmm. And for her to win this with perfect completeness, she needs to use the strategy that we talked about before. So what does it mean? It means that she has in her hand many EPR pairs, and she needs to measure these EPR pairs either according to the X measurement or the Z measurement. So when I'm doing this, I'm only using one of these 4 brackets. When I'm actually going to compare, I'm only using this. So I'm going to force Alice either to measure her left qubit according to X, or her right qubit according to X, or her left qubit according to Z, or her right qubit according to Z, for any pair of qubits that she has for any copy of the game, right? For any copy, she has a pair of qubits that is only for this game.
Okay.
Okay, great. And now I want to, okay, so I'm giving you the flavor. I'm cheating a bit here, but I don't want to get into where I'm cheating, okay? Now I want to send Alice, again, now Alice is the variable player. I want to send her a list of variables, but all those variables will be...
Michael, I really don't understand what is going on. Can you take one step back and explain, in very broad terms, what it is that we are doing now? I lost you. I mean, I understand each and every word that you say, but I don't have the
constructing a game. I'm constructing a game.
Yes. The purpose of which is what?
The purpose of which will be to, okay, never mind the purpose. I'm constructing a game which is which consists of 4 miniature games.
Okay.
The first miniature game is just playing 2 empty copies of the Magic Square game.
Okay.
Is this okay up till now?
Yeah, but why are we doing this? Where are we headed?
So
can I try to explain what I think might be the point?
Please.
No, I want to explain it. And then if I'm not good enough in that, you will do it. You remember, Nati, then in Guy's protocol, we need to send a point and a line to the players.
Absolutely.
I want the players to measure their own point and line.
Okay.
I want to send them questions that force them to measure a point and a line in such a way that the point player knows only his point and the line player knows only his line.
Okay.
Great. I'm doing my first try.
Okay.
The way I'm going to do it is use the fact that the Magic Square game is a self-test, and somehow manipulate. So I'm going to use this fact to force the players to do what I want, to sample a point and a line.
Okay. So the big purpose of this is to really make the game leader redundant. No one sends them, they serve themselves. Right?
Okay, so it's half true because I need to send them questions that force them to behave.
They're the ones, the sampling is do it yourself. It's not somebody.
The sampling part is only theirs. I'm not sampling the point and the line for them. they sample their own point and line.
Okay. And you want to manipulate them so that this is what they do and they don't play tricks with you.
Exactly.
Okay.
And the point is that if you want to sample a point, then you have to measure on the X basis. And if you want to sample a line, you may have to measure on the Z basis. And you want to make sure with which basis they measure. Is that correct?
This is kind of the idea. This is kind of the idea. There is a problem with doing that because you want zero information to leak from one to the other. So
Okay, but the point now is that you're going...
Dorit, for your remark, it would have been better if I could have forced the players to ignore some of the qubits, to not use these qubits. And this is why the identity there was important. So it enables me to force them to not use the information coming from this qubit when they are answering this question.
Okay, but just to try to understand the big picture of what you are just explaining in this slide, is that you basically, the players are going to have two types of particles or states. One type they're going to be using in order to sample their points and lines, etc., and do what Guy was trying to tell them to do. But
Right.
then this is some subset of particles. The
Right.
other subset is going to be used just so that we know what's going on in that other subset. And this is and the second one is going to be used to play magic squares.
No,
And
I want them to be the same particles.
And they don't know which one it is, but the way they don't know which one it is because otherwise they will be able to cheat. But essentially, we're thinking of this as the magic square particles are used to force them in order so that we know that what they do in the other particles is correct.
Okay, so you can think of it that way. Yeah.
Okay.
So the fact that they need to win the magic square game enables me to force them to conduct the measurements I want them to conduct on their particles.
Okay.
And I'm trying to explain how to do it. So this is exactly what I'm trying to explain. How can I force them to do these measurements?
Maybe it will be helpful if you tell us they share 4 MT EPR pairs. They also share more qubits.
No.
Oh, so they share just these 4 MT EPR pairs, and some of them will be used for the magic square games, and some of them...
So my claim is that the 4 MT EPR pairs come in pairs, right? So there is the first pair, the second pair, and there are 2 MT pairs of pairs, right? This pair is used for magic square 1. Magic square 1. This is used for magic square 2, and so on. Okay? Okay, so to win the first copy of the magic square game, they need to use the first EPR pair. To win the second magic square game, they need to use the second EPR pair, and so on and so forth.
So, yeah, let me just interrupt.
And you can do it in a way such that they actually need to use these many EPR pairs, okay? There is a way to do it. You just sample, you don't play all the 2 MT magic square games together. You play them, no, but you can play always all of them together, right? Okay. This forces them to use this kind of thing.
I think what Dorit asked was the following. Yeah, you play several magic square games in parallel, and that forces the players to play according to a specific strategy.
Yes.
But then you want them to play, you want one of them to play according to this strategy, so he will or she will choose like bits of a point or of a line.
Wait, I'm coming to it. Just for now, I'm just stating.
Wait, Michael, give 1 minute, just a moment.
So what Dorit asked what Torit suggested to use the fact to actually not play the magic squares on all the instances at once. Play magic squares on a random subset, and on another subset, send the questions and use the answers for something else. That's a valid way to do it, but that's not how Michael is going to do it. What he's going to do instead is, with some probability, play the magic squares on all the coordinates, but with a different probability, Alice will get the questions as if they were the magic square questions, but Bob will get other questions entirely. And so you play the magic square game with probability, I don't know, 1/5. And then with probability 1/5, you play a different two-player game, but where the questions to Alice have the same distribution. So Alice still thinks she's playing the magic square game, so she has to use the same strategy, but then you ask Bob something else.
But you ask Bob something else about the same qubits.
Yes, so you ask Bob the same, something else, that such that in order to answer successfully, he will have to use the same qubits.
And he will use those qubits to sample, for example, a sample point.
Yes.
Okay.
Right, is that true, Michael?
That is very true.
Okay.
Thank you.
Okay, great. So now
you shouldn't feel bad about this. I certainly, there are many things which I don't understand, and only by discussing these things together, you know.
No, this it's good discussion. אני מתוסכל רק מזה שאני לא מצליח להסביר את מה שגיא הסביר בקלות.
You know how many years he has been teaching and how many years you have been teaching. It takes time, you know, it's okay.
אני מדריך בנוער העובד מגיל 16, זה כבר 15.
Not the same.
Okay, so you're entitled to feel bad.
Yeah, I am feeling bad. Anyway.
Oh God, you're doing a great job.
Let's go back to the game. So now, after Guy's explanation, we see that for Bob, okay, so now Alice gets this question that comes from the magic square game, and Bob gets a question from this mini game that I'm highlighting here by the orange highlighter. And to win this game, he needs to do two things. He needs to measure the empty qubits that comes from the magic square game. So the first empty qubits, like the first qubit here and the first qubit here, from there is here empty pairs of EPR pairs. And Bob needs to measure all of them according to the Z basis. And the way we force him to do it is exactly how Guy said. We check that it is consistent with Alice's answers. And Alice wants to answer according to this exact measurements because she wants to win the magic square game. She doesn't know whether she's playing the magic square game or playing against this sample point game. So Bob must be consistent with it. And then the answers...
Michael, can you define better what it means to be consistent? Because
it means that
Alice
has answers, +1, -1, -1, +1, right? Alice gives answers to the brackets that she was asked.
But in some brackets, she was asked about her second bit.
Yeah, so I'm not caring about the second bit. In each EPR pair, I'm asking only on the left bit, okay? So I'm using only the left one. I have redundancy of factor of 2.
So when you send questions to Alice, you send question, at least for this application, you send questions from these upper left 4 blocks.
Yeah, I'm sending actually only this thing. You can think that I'm only sending...
Oh, so you are only using the 2 blocks where she's measuring her own bit, the left bit.
The left bit.
Okay.
And when I'm sending sample point to Bob, I'm sending in the first empty Magic Square games, I'm sending Alice this question. And for Bob to be consistent with this thing, he must use the same measurement on the first empty qubits coming from his part of the Magic Square game, right?
Okay.
He must have these copies of qubits because he also wants to win the Magic Square game, because with some probability for 1/5, for example, in your case, he will be asked for the Magic Square game.
Yeah.
So he prepared these qubits, and to win this mini game, he needs to measure all these qubits according to the Z measurement. Okay? And this defines a point, right? We have now empty plus and minuses. We can define that the +1 is 0 and the -1 is 1. And then we get some string. This string is exactly long enough to define a point in f2 to the t to the m. And this defines a point. But I want him to send me another piece of information. I want the point player to do this measurement, to be consistent with Alice, and to send me a value in f2 to the t. In this mini game, I don't care about this value. This value is not checked in this mini game, but it will be checked in this mini game. So I'm constructing here a web of mini games such that maybe for some mini games, you check only part of his answer. And for other mini games, you check another part of his answer, and not necessarily ever check all of his answers at once. But for him to win both games, he needs to both to sample a point, send me the point that he sampled, and add a value in f2 to the t.
Can you say how you want him to sample this value? Although, I mean...
Okay, so at the end, it will be exactly a value in the point versus line game. Okay, so at the end, I want him to send me polynomially many values. And these are exactly the polynomially many values in your protocol, Guy.
I'm not sure I understand. First of all, he uses some measurement to send this value.
Say again.
He will use some measurement to find this value that he's sending. So right now he can do whatever he wants, but in the future you will actually
at the end. Okay, so my claim is that what happens in this mini game is your protocol. The sample point player will send me a point and polynomially many values. The sample line player will send me a line measured according to the Z measurements on that comes from the Magic Square game. And he will also send me polynomially many polynomials.
Okay.
And then I will check only in this mini game, I will check your protocol. I will check all these zero and subcubes and these things.
I see. So there's no...
And this enables me somehow to cook
so this additional value... So this additional value, this is not part of this weird game that we're playing in order to make them sample something, but
yes,
we interpret the first part of Bob's answer as a point that he sampled himself. And now we ask him, okay, so if this is the point that, if this were the point that I asked you about in the MIP, in the original MIP protocol, what would be the value that you would return for that point.
Exactly. This is exactly how do I interpret this thing. And actually, maybe it is better to say polynomially many values, no, not polynomially many values, because in your game, the point player sent me polynomially many values back, right? So now I interpret these polynomially many values as the evaluation of polynomially many polynomials at the point that this player sampled for himself.
Okay, so at this point, at this time, we don't have to care about this. We have to care, there is this protocol that we are trying to simulate in which one player gets a point and the other gets a line. Here you already forced the first player, you forced Bob to sample the point himself instead of you sending him the point. And then you just tell him, okay, when you give me that point that you sampled, also answer whatever you would answer if I ask you this point in the MIP protocol.
Yeah, exactly.
Michael, is there room for a question here, or?
I think we are done for today. Like next time I'll explain how you actually do it, because the Magic Square game has some problems. But at least okay, the idea here was pronounced. I don't know. Yes, Dori.
Yeah. Okay. There was somebody said that it's a web of it's 4 miniature games. I only see 2. There is the Magic Square game repeated, I don't know how many times, 2 empty times. And there is the sample point versus sample line game.
No, there is also the mini game where I check that the sample point is consistent with the variable player of the Magic Square game.
But this is not a game.
This is a game. Sometimes I'm sending, think of it as the following. I am sending one player the sample point question.
Okay, you're just treating this, I can view this as if there are two miniature games. And then since the 2 players don't know which game they're playing, I mean, they think they're playing a player who plays the same game, but actually he's playing the game, he's part of the other game.
So I'm thinking of it as a new game.
Okay.
And you compare, and this new game consists of, on the one hand, questions from the miniature game Magic Square, the other from the miniature game Guy's Protocol. But the players a priori know that potentially I can also do this cross-checking. So you remember that when we define a game, we need to give all the rules beforehand. So I cannot surprise them. I will tell them beforehand that maybe I will send one of them the variable question and one of them the sample point question, and I will cross-reference that they are consistent.
Yeah, I think it's more, it's conceptually, I think it's nicer to think about it as 2 games which you just cross between them. But
this comes from the MIP star is equal to RE notation. They use graphs, and you think of the graphs as either like any vertex is a question, and the edges defines to which other questions you can compare this question. So this is the constraint question. This is the variable question. I can compare the variable question also to the sample point question. And I can compare the variable question also to the sample line question. This way, the fact that I'm using variable against sample point and variable against sample line enables me to check that they actually sample a point and the line which intersect. This is the way I'm verifying that the point and the line intersect.
Yeah, and only this edge, only this final game, this is the MIP. This is where the MIP game is played.
Right. But the only plus here is that I didn't measure the line and point for them. They measured the line and the point for themselves. This was the upshot. There are many downshots here, I don't know. This is a much more complicated game than just playing the MIP game. But we have been able to I don't know how to say it, to force them to sample their own point and line in this using this machinery. Now you can tell me that sampling a variable question takes empty time. And we said that our lines live in F2 to the T to the M. So the questions here are still exponentially long. So for this is a bad game with respect to the fact that we want to shrink the length of questions. And also, actually, this is not a robust game. And there are many problems with this protocol. This is not a good protocol. But at least for perfect completeness thingy, you know that for them to win with 100% probability, they need to sample their own point and line, and they need to answer the MIP game accordingly. So I will give time to questions, but I will say a small thing before we finish. Next time we will replace this game, the 2MT parallel magic square games, by a much better game. And this game will again be compared against some sample point and sample line. And for them to win, now it will be also robust. And for them to win, they will need to sample a point and sample a line and play the MIP game that Guy gave us in a good way. And then we will solve at least the question reduction part, because all questions here will be polynomially long.
Oh,
So how many more times we are going to meet this semester?
So this is the pan-ultimate meeting of this semester. And so we meet next week, and then after that we meet only on March. I think that if someone wants to do some reading group that keeps on talking about these things, we can, but formally we only resume our seminar on the second semester.
After next week.
Yeah, so we meet next week, and after that, 2 months later or something.
So in the meantime, we go to Alex's.
Yeah, Alex's seminar is resuming on this Wednesday, so we highly encourage you to come to his stability seminar. Any questions? But I think like the formal part is over, but
I have many questions, but I'm waiting till the formal part is over.
Okay, so we finished the formal part.
Till I can bombard you with questions. So I guess in terms of how to explain things, I think I got a bit lost. I mean, I more or less understand the picture, but still there are too many holes now. I got a bit lost in the sense that how things look if I just look at 2 miniature games. Okay, forgive me for looking at it this way of 2 miniature games with crossings between them, but I just want to see. I understand the magic square game. We have 4 MT EPR pairs, and I understand the sample point and sample line game basically are played with the same qubits. You have 4 MT EPR pairs, and you need to play. The players need to use those qubits in order to play this game.
Because of the cross checks, right?
I mean, I just want. Let's just look at the situation in which the game that is being played by both Alice and Bob is the sample point versus sample line game.
Yeah.
Just this game. I want to understand it because there's something I don't understand there. So if I just look at this game, they still share 4 MT EPR pairs.
Right.
Their questions, how do their question look, and how do their
I send one of them sample point and the other one sample line.
And then what do they? So you send them a sample point.
They should answer with the sample point player needs to send a point, meaning empty bits, and afterwards he needs to add polynomially many values in the field F2 to the T.
But if he is honest, with what basis does he need to? Both of them need to just measure in the basis Z?
Yeah, so I didn't explain how the line player works. I only explained that the point player measures like half of the first, the left part of half of the EPR pairs with respect to the Z basis, right? And he needs to use that measurement to answer what is his point.
Okay, and the line, what does the line guy need to do?
Okay, so this is a bit more complicated, and at least here I cannot answer it in a way that that hides the line. Okay, so the easiest way the line player can measure his thing is just measuring all of the EPR pairs, all the left coordinates of the EPR pairs according to the Z basis.
But then if they don't need ever to, if in order to play the sample point and the sample line game, this game that we're talking about, this miniature game, with just Z basis, they don't need quantumness.
Wait. They do need quantumness in
So where?
If to play the Magic Square game.
No, but the Magic Square game is enforced, is used just in order to check that they measure in the right basis. If they only need to measure in the Z basis, who needs the Magic Square game?
For me to force them to measure by themselves the qubits. Now, I would want.
If you only need to measure them to measure in the Z basis, both of them, then just give them classical strings. You don't need to force them to measure in the Z basis if you can give them classical strings.
Okay, so
No, the point is.
what do you mean if I can give them classical strings?
I mean, they can.
For now, at least for now, you are correct that I want, in some sense, the point player, the line player needs to not know what is the point of the point player. Otherwise, this is not a good protocol for me, right? If the line player knows what is the point of the point player, he can cheat. In the protocol that Guy gave us.
But then he knows, if they both measure in the Z basis. And
yeah, you are correct that at least in the way I just presented it now, the line player knows about the point, which is a bad thing.
Okay, so I still don't understand where. So that is one thing that I don't understand where the quantumness comes in.
I will get to it.
Let me also say that I don't understand also where sometime, I don't know, a few months ago in the beginning of this talk, you said something about polynomial versus exponential length of questions and answers. Right. Where did this go?
So it's not in, this is a bad protocol. I started with saying that. So this protocol is still exponentially long.
Okay.
But I want to replace the parallel Magic Square games by a better game, which has only the fact that the questions here are O of 1. I'm sending sample point or sample line, right? So the only problem comes, the length of questions come from, the bad length of questions come from the Magic Square game.
Okay.
I'm going to replace it by a different game that still forces them to share.
Okay. I'm okay with the Magic Square game, but I don't. Let's stick to this miniature game, the sample game and the line game. So you're saying it's still exponential.
It's exponential in answers. It's
right.
Of 1 in questions.
So we will need to reduce the size of the answers, right?
Yeah, this is true. This will be used by PCPs, but this is I'm only in the question reduction part.
Okay, good. Okay. And then the other thing which I still don't understand is where does the quantumness, where is it needed in the completeness? In the soundness, I understand. Okay, so maybe you need to force this.
It comes in the completeness because the way that I force them to measure their qubits according to some basis is using a game which is a self-test, and to win in
No, but you don't need the game with a self-test if all you need is to force them to measure in a single. For completeness, you can assume that everything is classical.
No, this is not true. They can lie to me.
Completeness.
Can I say something?
Yeah, but I have this part. Like you can say, okay, I want to ignore the Magic Square game, but you cannot ignore the Magic Square game because it's part of my game. there is a positive probability that I will send them the magic square game, and then they need to use entanglement. You are correct.
Okay.
This,
Okay, you're saying that since you need to use entanglement for the soundness, then for completeness you also need to use that. That's what you're saying. But essentially,
you need entanglement to correctly answer the constraint versus variable game.
Okay, me and Guy talk together. Maybe Guy talk, and then I'll say what I want.
You need entanglement to to achieve perfect completeness for the sample point versus sample line game?
No.
No, just for the constraint versus variable game.
You mean the magic square, you mean?
The magic square game.
Yeah, of course.
But then it means that the variable player plays using a quantum strategy. Even when the game is not variable versus constraint.
No, I got it. I think what I said, please give me a mark if it's correct. Okay. What I said is that for soundness, you have to use magic square games. And therefore, even the complete, I
don't understand what you mean by for soundness, you need to use magic square.
So entanglement was introduced in order to enforce soundness against cheating provers. Right. And therefore, magic square is sort of, you cannot ignore it. And since you cannot ignore it, also the provers that play honestly have to have entanglement.
Yes.
Okay, exactly. Thank you. Okay, I think that answers my question.
Yeah, so but you don't need to use the word soundness here. The players need to use entanglement to win the magic square games. And because they don't know if they're playing the magic square game, they have to continue playing with...
Yeah, I understand.
Okay.
Okay, good. So, okay, so then the reduction of the size of the answers is going to come with sometime later with PCP, and it's sort of, it's a black box of, you don't really...
Yeah, but forget about the answers. Even the questions here are problematic because you have to ask...
Yeah, for the magic square.
You have to ask empty questions to get empty...
Right, but that part I understand. That part is the low degree self-test. So
quantum low degree self-test, exactly.
This is where I know how to reduce it. Okay.
Okay.
Cool. Yeah. Okay. So yeah, exactly. I'm going to exchange this the parallel magic square game by this the quantum low degree self-test and.
Okay, great. Good. Thank you very much.
Okay.
Cool. So see you next week.
Michael, can I ask you something? So I have two questions. First is, if I understand correctly, and correct me if I'm wrong, just to make sure I understand it. In the same way that we need the constraint versus variable to see that the variable player uses the magic square game strategy, in the same way I have the variable versus sample point and variable versus sample line in order to make them consistent between point and line, because I won't be able to check that because they use something between them and I won't be able to see that, right?
I will be able to see that because part of the answer will be
it will be the point and the line.
Sampled line, and I can check that.
Oh, right.
But I would not be able, the point is that I would not be able to check that the line and point were sampled uniformly. You want
and for that I need the variable versus sample point and variable versus sample line.
Forcing them to use EPR pairs and then measure them according to the Z basis, use their answers to these questions to answer the sample point and sample line questions. I'm forcing them to use the uniform distribution over line, and then the uniform distribution over points on this line.
Great, thanks. So the other question, great, so I understand that now. But the other question was about making Alice actually not know whether she's playing against the quantum, the magic square game or with the sample point, right? When you said when we have her play against the sample point, I'm only going to use the upper left and the middle boxes of the square, of the magic square.
Yeah, which is a legitimate question as part of the magic square game, right?
Yeah, but if she gets empty questions of only that kind, it's very unlikely that
Yes,
they would.
You're right. This is a bad game in this sense as well. Like she can guess that whenever she gets only Z's, probably she's not playing the magic square game, and she can use this probability to somehow. But this is. But I talked only about perfect completeness. I didn't talk about soundness now, right? I didn't tell you that this is a sound game. Actually, it's a very not sound game, as you just mentioned. But to win with 100% probability, she needs still to be like, there is the probability that I'm asking the other player the magic square game, and for her to win always, she needs to be consistent with this possibility as well.
Right.
Yeah. So.
But for that, you don't even need to fool
in
her.
a real application, you would have to hide the questions in a way that you will not be able to tell that what you're actually interested in.
Yeah, and there is a way to do it. Like we need to replace the parallel magic square game is not the correct game.
Okay, great. Thank you very much.
Okay, see you.
Bye.
Bye.